So for those of you that tuned in last time, welcome back. And for those of you that are new to this webinar series, welcome. So we're on part 2 of Exploring Engineering Fundamentals, and today we'll be talking about Introduction to Vibrations with specific examples in free response of spring mass systems and harmonic excitation. So today I'll start with a quick recap from some of the challenges we discussed last time, but just a reminder that all of our webinars are posted to both our recorded webinars page or on our YouTube site, so you can go back and revisit any previous content. So there are many challenges facing engineering education. Class sizes are consistently increasing with the demand for STEM graduates, yet funding is decreasing. There's a disconnect between the engineering curriculum and the skills that industry requires. And with technology changing so rapidly, textbook examples quickly become outdated. So instructors need to keep content fresh with relevant and current examples that students can relate to, while keeping them motivated and engaged in the material. On top of that, engineers not only need to be experts in their own fields, but the lines are getting blurred between disciplines, so they also need to have an understanding of other areas, and they need to keep well abreast of emerging technology, all on top of an already heavy course load. So there are trade-offs to be made, and instructors need to find a balance of what works best, whether this is in theory versus practice, open and closed-ended problems, individual and group evaluation, and whether that's in a traditional lecture or active classrooms. So on the flip side, how about in industry? So engineering products are becoming increasingly complex, and organizations are building multi-domain systems. So as an example, the line between electronic and mechanical systems in cars is becoming quite blurred. Today's vehicles are now complex mechatronic systems, essentially. So given this trend in other areas too, the question is, how do we build and test these multi-domain systems, since traditional modeling techniques are not necessarily effective? So more and more organizations are turning to physical modeling, and industry is crying out for graduates with these skills. So students need to be prepared to meet these new industry demands. So what is physical modeling, you might ask? So model-based design, sometimes referred to model-based engineering, is physics-based modeling or physics-based software modeling of systems. So instead of modeling equations of a system, it's possible to directly model the system itself with all of its associated physical laws. So current, voltage, resistance, mass, velocity, and so on. So when used in industry, it shortens and improves the engineering design cycle, and rather than build and test physical prototypes, physical modeling is much faster, it's cheaper, safer, and this is why there's a real need for people with these physical modeling skills. So on the education side, physical modeling helps bridge that gap between theory and reality. So the physics is already embedded in the models, and educators can focus on that application of the theory. So where do we fit in here? Many of you may be familiar with Maple already. It's a rich and interactive environment for describing, analyzing, visualizing, and solving mathematical problems. So unlike static and abstract equations that you get in a textbook, Maple brings those concepts to life with multiple analysis options. Now, paired with that, MapleSim is the multi-domain physical modeling and simulation platform that lets students build and interact with engineering systems to connect theory to physical systems that they can understand. Well, MapleSim is unique because the models are based directly on the governing laws of physics, and it's built upon Maple, our powerful symbolic computation engine. So this means that while students are modeling systems, rather than modeling the equations of systems, all of the system level equations are easily accessible by instructors and students. And using these equations, they can carry out professional and in-depth analyses that are traditionally not possible in the classroom. So students are able to gain an insight from these complex engineering models, letting them see that what they are learning about in the classroom really does matter and has an application in the real world. So in the following demo, I'll show you a combination of Maple documents and how they can be used alongside MapleSim models to demonstrate a few engineering principles. In this case, we'll focus on vibrations, as I mentioned previously, and we'll look into free response and harmonic excitation. So here we are in Maple environment. So starting with a basic spring mass system, here I have my Maple document. So if we go through, we start out with basic spring mass model, and we're going to build on the basic theory of the physics here. So we can see we insert our equations. And I'm not going to get into the math or the physics. That's not what I want to show you today. More of what the capabilities of Maple and showing the integration of Maple and MapleSim. So here we start to show examples and demonstrating problems so that students can start to build what they're learning. So we showed the equations and starting to use those equations within a problem in MapleSim. So building up and having a plot to show displacement, velocity, acceleration, starting to bring in those visualization and to show meaning in those equations, having more examples, and being able to have these 3D visualizations is really key to an understanding. So something that they can interact with, and this can be customized. So right now it has a surface wireframe, being able to change the style of the lines, the color, the transparency, and whatever else, even down to the lighting. And then the plot from previously, your displacement, velocity, and acceleration. Again, being able to interact with this, with your, being able to vary the gauges and look at the different initial conditions and parameters of the plot to see the different effect on what the mass and the different coefficients have. These can also be manually changed within here as well, rather than moving them here. Adding in images to show the examples, and continuing in to add just like a textbook would, but with more interactivity. Now we start to show what the examples would be in MapleSim. So how we've laid this out would be to show an example with a problem statement. So for example, a component of a machine is modeled as a pendulum. So in this case, I'm going to go through 4 different parts. So free response parts 1 and 2, and harmonic excitation part 1 and 2. And I'm going to use, aside from the last example, a pendulum throughout to demonstrate. as it's the most simple example I can show you right now. But for a student, being able to build up the various components, constructing the model, and walking them through what they would need. So here, having the different multi-body components, connecting the components and showing them, okay, this is what it would look like in the document. Now if we jump into MapleSim, so this is the MapleSim interface, so that's the second one. So here, having a description of what they should expect and running the simulation of the model. And these components are just drag and drop. So when a student would come into here, they would be looking for each of the components within the MapleSim interface, build it to look like the configuration from the Maple document, and run their simulation. So I'll show you the animation first. So here we have a basic spring pendulum. And we also have the plots to go along with it. So if I run this again, you can see each of the plots over time. So looking at your different probes, for example, for acceleration, and your other different parameters that you're wanting to check in on. You can also, as it runs, toggle in on what value at each different point. And this can be helpful, so depending on what problem statement is given. So in this case, derive the equation of motion and find the natural frequency of the system, also find the amplitude of the angular velocity. So when a student is trying to solve for this, they can use the MapleSim, run the simulation, and use this as a more practical way to figure out the answers that they're looking for to derive their solution. You can also include videos so that when they put it together, they know what it is their expected outcome should be. So part 2 is building on this again. So our first example was an undamped system. So we know that this is not the case for most systems in the real world, and so building on that, adding damping to a multi-body system would be the next example. And so explaining in real-world examples what that might look like, so air drag, internal forces, and so on, and adding in those equations and providing those real-world examples for an engineering class is useful. So in this case, adding in these plots, the equations, and with the vibration decaying over time, as we would expect. And again, adding in these interactive plots with gauges that can be adjusted for the varying coefficients, either here or specifically this value can be adjusted too. And again, the same kind of example, so giving a problem statement, specifically for the pendulum. The example walks the student through what they need to do in MapleSim. Just another example here. MapleSim to construct the model with each of the various components, what menu options they would need to choose, what the resulting model looks like. And this can all be customized in parts to how much an instructor would want a student to see. So if you wouldn't want them to see the final model until later, and how much guidance would be required. So again, we see spring pendulum with damping. We can run that one. Sometimes they don't always pop up. I have to go looking for them. So as we can see, to be expected, it stops by itself, it doesn't continue to run. And the plots show the same thing. Our waves slow to a stop. I believe this one has a second example, and these examples are all online, posted to our website as downloadable content. So this is accessible. I'm not going to go through this one, but it's basically a bicycle suspension that shows spring dampers. So our third example, so harmonic excitation part 1, so this is referring to external force being applied and becomes popular, is important for engineers to learn, since it starts to bring in those systems that contain rotating masses, tires, engines, rotors, etc. This module in particular looks at single degree of freedom systems without damping, and part 2 again looks at those with damping. So continuing with the pendulum example. So again, looking through building up the base of your core equations, examining your theory, looking at each of your plots to drive home the principles, that you can play around with the different displacement time graphs. These plots are animated, and so being able to show those sinusoidal waves, and again here, so this one has a few examples that it walks through. So a spring mass oscillator and a spring pendulum. I think that's the two on this, and again a video. So again, walking through the same components. We'll run this one. So this one actually has a motor addition. So we'll see the change in movement on that one. We'll see our theta plot for that changes quite significantly. So you see the change here. Let me see your playback. So you see that very rhythmic motion and our theta plot for that too, and you can see over time as that animation runs. So our last example, back into Maple. So this one is with damp system. So part one covered the single degree of freedom system. But usually there's some kind of energy dissipation or damping. And so this module examines that type of system. Again, adding in the external force. As always, more equations. As I mentioned previously, all of the math that we're seeing in here, so our core engine is Maple. So right now we're just seeing the document side of it. But everything in MapleSim is run by Maple. Another interactive plot that we can play with. This one has several: a spring mass oscillator, spring pendulum, and with a motor, and a fun example for this one, another video, and a wind turbine example with quite a detailed problem statement for this one, as it's a more a much more complex model for this, but does detail how to be built, and has a lot more detail in the plots and if this one runs. But I have the example open for this. I'm not going to show you, it's basically the same as the last one. This one has the motor again, but is just a damped system. And finally our wind turbine example, which I'll run for you because this one's a fun one. But it's examples like these. I think the pendulum ones are important to show because they're basic, they're easier to put together. It's finished, it's just hiding. Easy to put together, but once the foundation's been built, adding these more complicated ones that take a little bit more time but have that real world tie-in, drive the concepts in a little deeper. So right now I have it at 2 times the speed. We can increase speed on these. We can open the probe plot, so that one's angular frequency. We can look at deflection. And we still have it running, so we can see over time how these are running. We can look at nearest point online. So again, these are helpful in looking for what our solutions are. This again. I get it going so fast that it looks like it starts turning backwards. But that's all of my examples that I'm going to run for today. I'm going to jump back into our presentation. So as we've seen from these examples, MapleSim brings clear value to students and instructors. For students, MapleSim can bring theory to life. It gives them that sandbox for reality where they can test out ideas, build intuition, in an industry that can take years to develop. They can test their understanding of concepts by building models, playing around with parameters and variables to see their effect and changes. I didn't play around with it too much, but with the pendulums you can change their mass, play around more with the effect of gravity, see what that does, play around with the spring, and so on. So it's quick and easy to extend or modify a model and rerun those simulations over and over. So for instructors, it saves time. You can deliver in-depth coverage of multiple engineering disciplines by turning from extensive lesson plans to interactive models, which are easy to update and change. So instructors can focus on the most important concepts and reinforce them in a meaningful way through modeling and simulation. And since MapleSim is a tool used for complex modeling and simulation in industry, instructors can be assured that they are bringing added value to their students' resumes for placement after graduation. So as I mentioned, our online resources. So exploring engineering fundamentals, that's what we're looking at today, but these are a compilation of Maple and MapleSim content broken down in different engineering topics. They are on our website. They're meant to provide instructors with an idea of what can be done using our products and can be used as a starting point. So all of those Maple worksheets, MapleSim, models, everything is available for download, not just for the vibration modules, but also the part 1 kinematics and dynamics, and the future content to come. And the MapleSim model gallery is a compilation of MapleSim models, not necessarily geared towards education, but these models can be used by instructors to motivate students of real-world applications. Finally, our recorded webinars, so webinars with ideas and inspiration for using Maple or MapleSim in the classroom.